All right, the last section we need to look at is graphs. And they give you the different steps they want you to go through to break down the graph of the function. And so first things first, I have a function f of x is equals to 1/3 x cubed minus 1/2 x squared minus 6x plus 4. Step number A, find the first and second derivative. F prime is going to be x squared minus x minus 6, and f double prime is going to be 2x minus 1. There we go. That's our first and that's our second derivative. Look at that. Step number B is to find the critical points. The critical points are found when you take the derivative and you set that equal to 0. Well, x squared minus x minus 6 equals to 0. You can either use the quadratic formula or factoring to get to the answers. I believe it is x minus 3, x plus 2. And so I get that x is equals to 3 and x is equals to negative 2. Those are my critical points. To find the inflection points, I have to set the second derivative equal to 0. And I take the 1 over, 2x equals negative 1, is equal to 1, sorry. Notice I'm not factoring here. You factor when you have a second order equation. And then I divide by 2, so x is equals to 1/2. So this right here is my inflection point. X is equals to 1/2. Now they want me to create a sign chart for each of those. So for step D, if I draw a long number line, in this number line I have a negative 2 and I have a 3. That's a critical point. That's a critical point. And I have my function f prime of x. Well, when I take a number smaller than negative 2, say for instance negative 3, and I plug it into this function, the answer I get is positive. And so therefore, s is going to be plus right here. Remember, I like putting lots of positives. When I plug in negative 2, it's 0. If I take a test point between here, say for example the number 0, the answer is negative. And then after this test point, it is 0. And then again, the graph is a third test point. The graph is increasing, getting larger and larger and larger. So that tells me then that the graph is increasing, followed by decreasing, followed by increasing once again. The number E, sign chart. So for number E, you go all the way across like so, and then once you go all the way across, you put your inflection point, which is 1/2, which is somewhere around here. And so this is your inflection point, I guess IP for inflection point. It's going to be 0 right here. And then you're going to have to plug in a number over here. By plugging, say, a test point of, say, 0. If I plug in 0 into this thing, the answer is negative. So the graph is first negative in terms of its second derivative. And then, test point over here, I get an answer that's positive. Say a test point of 10. 10 times 2 is 20 minus 1 is 19. That's positive. And so it means that the graph is concave down. Remember, that means the graph is bending downwards, while after 1/2 the graph is concave up. Remember, the inflection point is a point when the graph changes concavity. So the graph from this first picture, the graph is increasing and then decreasing and then increasing again. The information we get from this right here is the graph is concave down, bending down, followed by being concave up. We tie that together, and that allows us to graph the function, to graph our function, which is step number F. Now your sketch does not need to be accurate in terms of going through all the exact points. We just need for your sketch to capture the main ideas. So at 1/2, I have an inflection point at -2. Let's move that 1/2 a little bit closer. That looks more like a 1. So the 1/2 is right here. 1, 2, 3, -1, -2. And so therefore my graph is going to be increasing until it gets to 2, decreasing, switching concavity at 2, and then, my graph is concave down, concave down, concave down. 1/2 it switches and becomes concave up, concave up. And of course it bottoms out at 3 and maxes out at -2. And so therefore that tells us the answer to the last part of the question. At x equaling -t, I have a local max, and at x equaling 3 I have a local min. The other way of getting to this answer right here is using the second derivative test. Remember the rules for the second derivative. If f double prime at the value x is negative, you have a local max. If f double prime at the point is greater than 0, then you have a local min. And if f double prime is equal to 0, you have no result, inconclusive. And so if I take my second derivative, which is 2x minus 1, and I plug in -2, f double prime of -2, that's -4 minus 1 is -5. Notice that it's negative, so that tells me it's a local max. And then for the one at 3, f double prime at 3 is 2 times 3 minus 1. That's 6 minus 1 is positive 5. Notice that it is positive, and so therefore this is a local minimum. That right there is called the second derivative test. Alright. So we gotta do all of this again, but for a new function. Lots of fun in the neighborhood. So number 21, I have my function f of x is equal to 1/4 x to the 4th plus 2/3 x cubed plus 7. A is the first and the second derivative. That is x cubed plus 2x squared. The derivative of 7 is 0. The second derivative, f double prime, is 3x squared plus 4x. That's answer A, the first and the second derivative. Step number B, the critical points, is when you take the first derivative and you set it equal to 0. Again, a factoring argument is the best way to solve. So I factor out x squared. And that leaves me with x plus 2 is equal to 0. And so I get that x is equals to 0 and x is equal to -2. Those are my only two critical points. Number C, the inflection points. And to get your inflection points, you have to take the second derivative, which is 3x squared plus 4x, and set that equal to 0. Again, here I can factor out x, and that leaves me with 3x plus 4. And so I get that x is equal to 0, and I got that x is equal to negative, let me work it out, that's -4/3, but 3x plus 4 equals 0, 3x equals -4, x equals -4/3. So those are my inflection and critical points. Gotta create a sign chart for the, so part D, show your number line. My sign chart has on here a -2, It has a 0. So a test point, say negative 5. If I plug negative 5 into this problem, that's going to be positive. That's negative 5 squared is 25. 25 times negative 3. Yes, negative 75. So it's going to be negative until I reach the first critical point, which is 0. And then a number between negative 2 and 0. So a test point of negative 1. If I plug negative 1 into this equation, that's negative 1 squared times 1, which is positive. So this right here is positive. Then I have my next critical point, which means that it is 0. So 0 is a critical point of 0. And then, let's say a test point of 2. 2 squared is positive. 2 times 2 is 4. So this is also positive. And so therefore, this is equals to positive. Let me show that again, just to make sure. I'm taking the number 2 and I'm plugging it into the first derivative. So that's going to be 2 squared times 2 plus 2, which is 4 times 4, which is 16. This is a positive number. And since I took this 2 from this test point right here, it means that all of these in this section will be positive. And you're taking the number and you're plugging it into the derivative, the first derivative, f prime of x. And that's how we get all those signs right there. Going backwards, going backwards. So I guess I should put f prime right here of x. So that means that this function right here starts out decreasing, and then it is increasing, and then it is decreasing. Oh, no. And then it is increasing again. This function goes down, then flat, then up, then flat, and then up again. So, number E, sign chart to the stars. And it's a sign chart for the second derivative. So this graph goes through negative 4/3 and then 0. And this is on f double prime of x. This is an inflection point. This is the second inflection point. So I take a number that's less than negative 4/3 and I plug it in. Say test point of negative 10. If I take negative 10 and I plug it into this equation right here, the answer I will get is negative 26 times 10. Times negative 10, so that's positive 260. So this is plus. Inflection point is 0. I believe negative 1 is between these two. If I plug in negative 1, have negative 1 times positive 1, so that's positive. Oh, that's negative time. Again, so that's negative 1 multiplied by 3 times negative 1 plus 4. Negative 1 multiplied by negative 3 plus 4. Negative 1 times positive 1. That's negative 1. So therefore, these are all negatives. Again, you're taking it and you're plugging it into the appropriate equation. Last, at the critical point of 0, again it's 0. And let's say I take a test point of 2. When I plug 2 in, that's definitely positive. And so then that tells me the graph is concave up. Can't spell concave today. Concave up, then concave down, and then concave up again. So this graph is going to bend up, and then it's going to bend down, and then it's going to bend up again. So that kind of gives us the contours of what this graph kind of looks like. These two pieces of information. And so then that allows us to graph the function. So we gotta be a little bit careful. This graph's a little bit more complicated. -2 and 0 right here, and then -3/4, -4/3 right here. So this is my CP, this is my IP, and this point is both an IP and a CP. And so the graph starts decreasing, but it's concave up. So the graph starts going down, but it is bending up. It switches right here, and then it makes maximum right here. See right here, it's concave up, then concave down, and then it switches and it goes this way at 0, like so. So this graph right here, I have to go ahead and describe the local maximum, minimum at each point. And so at x equaling -2, we have a local min. At x equaling 0, we have a saddle point. It is neither a local max nor a local min. If I were to use the second derivative test, the second derivative is f double prime at -2, which is 3 times -2 squared plus 4 times -2. This answer should be positive, right? And so that's 2 squared is 4. That's 12 minus 8, which is 4. So it indicates a local min. And then f double prime at 0 is 3 times 0 squared plus 4 times 0, which is 0, which tells us the test is inconclusive. Whenever we're inconclusive, we have to look to the graph to determine whether we have a local max or min, and then we can see that the graph is neither local max nor local min, because after the critical point, the graph keeps doing what it was doing. So it's increasing, it goes flat, but it increases again, and that's the hallmark of a non-max, non-min point. All right, last question. This is number 22 and number 23. Those that simply say, look, I'm going to give you a sign chart, go ahead and graph the function. So for number 22, -2 is a critical point, 0 is a critical point, and 2 is a critical point. And what the sign chart tells me is that the graph is decreasing, constant, increasing, constant, decreasing, constant, and increasing. Right here. And then at the inflection points, I have an inflection point at -1. Sorry, IP. And then I have an inflection point at 1. And those inflection points tell me if the graph is going to change concavity. And so with that right here, you can actually kind of see what's going to happen. The graph is going to bend down, switch concavity here, switch concavity here, go this way. So it looks like a fancy W. Basically, the inflection points help us bend the graph in the right direction. When I get to this inflection point right here, the graph starts going the other way. That's what the inflection points are there for. So it tells us when the graph starts bending from going up to going the other way, from being concave up to concave down. That's how inflection points help us. For these, I mainly go by increasing and decreasing, and then I use the inflection points to help me bend the graph in the right direction. All right, number 23 is a little bit trickier. but it's the same idea. Number 23, I first start out by putting together the sign chart for the first derivative, -4. The graph is increasing, and then -2, it's decreasing until -2, and then it's increasing until 1, and then after 1 it's still increasing. That looks like a saddle point, and at 2 it is then decreasing. So the graph is, that's a 0 right here. So graph is increasing, flat, decreasing, flat, increasing, flat, increasing, flat, and then decreasing. So I have the basic idea of what the graph already looks like. You can kind of look at it and see. And of course, the inflection points sit exactly in the right places to help the graph bend in the way we actually expect graphs to bend. So at -3, I have my first inflection point. So the graph is concave down, 0 at the inflection point, up until -1/2. So -1/2 is right around here. The graph is concave up, 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 0. That's the inflection by 1/2. And then after 1/2 until 1, right here, the graph is concave down, negative, 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 inflection point 1. Notice how those two coincide. That's normally another indication of a saddle point. And then at 1/2, again the graph is concave up, 0. And then the rest of the way the graph is concave down. So that tells me that the graph starts at concave down until it gets to -3, where it ends, goes flat right here, concave up until it gets to 1/2, concave down, till it gets to the saddle point, and then it's concave up, and then concave down again. I should have topped that at -2. A little bit off, but right here. Right. And then if I just remove the little green lines, I will have the graph of my function. There you go. Concave down, flat, concave up, flat, switch to concave down, saddle point, concave up, switch back, concave down, flat right here. And there you go. That's your graph. Good luck.